basically just to be a dumb pipe between the applications and the smart cards. But it also allows applications, each application in turn, to have its own control. Otherwise, you'd have a bunch of gibberish if a bunch of apps were trying to send commands to the cards. I mean, these things are dirt simple. They're real dumb. So you have to have some logic in the PC to make sure that the communication is successful. S-Card Server does that. And then the 4 and 5 arrows branching out. 5 is an example of the data flow to this system service, for example, that always reads data from the card when you insert one. 4 is showing the data flow to, for example, a smart card aware application, such as the one that I wrote to demonstrate fuzzing the middleware. Okay, so referring to that block on the right, the bottom box there, WinScard Client, that's just the API, the Windows API for sending commands to the smart card. So it's basically just an RPC shim over to S-Card Server. Okay? But because that interface is so well defined, it's a really easy way to put a hook in and perturb that data flow. And that's exactly what my fuzzer does. So in other words, my fuzzer kind of inserts itself between the WinScard client and the smart card middleware, the piece provided by the vendor, so that in some cases what the middleware is receiving is actually not what the card sent, it's what I put there. And then just to complete the picture, on the right-hand side there, the top 2 boxes, I'm a lazy developer, which I think is a good quality for all developers, by the way. So I just wanted to make this as simple as possible. And there's some kind of high-level crypto APIs in Windows where you can basically just call a single API and it'll load the smart card and initialize the whole stack and everything for you. So I'm just calling that API to trigger the whole demo. Any questions about that? Okay, so let me show you the demo. This is actually pretty simple in principle, but I'm going to be showing it in the context of a debugger, so it gives it kind of a sexy, really technical, scary look, you know? And of course, since I worked at Microsoft, the Windows debuggers are my preference just because that's what I learned, but obviously you could do this in any debugger. Okay, so let me just explain a couple things of interest here. S-Card Fuzz is my demo program. The demo, I think at the end of this, you might think that the demo is a little bit contrived, but it's really not. And so give me a second to explain why that is. And finally, look at the last static dependency here before I run the program. This is the DLL that I wrote to do the hooking. So if we go to the 3rd static dependency, recall that this is the client API for sending commands to the smart card and receiving them. Okay? I'm going to use my DLL to go into the vendor's piece, the vendor middleware DLL, and replace the import for smart card transmit from WinScard with my own smart card transmit, the evil smart card transmit. And then in some cases, I'm just going to call directly over to the built-in one and not change anything. And in other cases, I am going to change stuff to see what happens. So that was it. I go to the debugger, and the application crashes. Access violation. What happened? Let's see. The reason that's interesting is that so you can see here S-Card transmit being called a few times by the vendor middleware in response to that crypto API call that I made. And actually, I like that the display is wide. By the way, I think you guys can probably see that. Everyone can see that, right? Okay, maybe that side's blurry. Well, sorry about that. Anyway, the first command that is always sent to the card whenever a card is inserted is to read this file called card ID. And it doesn't matter what kind of card it is. So this hack applies to any vendor's card that's compliant with this smart card stack. My point is that you can predict the commands that are being sent. So in response to receiving this command, the smart card receives this command to say, hey, I want to read the card ID file, and I want you to tell me how big it is. So here's what the card sends back. The card says, hey, I have a valid response for you. I believe what 61 is, I have a valid response, and it's 1 byte long. And it says, OK, you need to read 1A bytes, which is what, 26 bytes decimal, right? Now, I happen to know that the card ID file by spec is only 16 bytes long. It's a GUID, basically. It's intended to uniquely identify every card. For some reason, there's a bunch of metadata that this particular implementation includes with that 16-byte file. So there must be 10 bytes of metadata that it also wants to return. Okay? I lost my mouse here. So then this command is the application saying, or specifically the middleware saying, OK, well, go ahead and send me that 26 bytes. And here's what the card says. The card says, OK, here you go. Here's a bunch of metadata. And then here's the actual interesting payload of that file. Here's the 16-byte GUID. And here is presumably a length tag, 16, right? And then the last 2 bytes, 9000 in the smart card speak, means everything's cool. I'll say up front that I actually don't know what all this metadata is. I mean, I don't have access to this vendor's code or anything, and it doesn't really matter, quite frankly. Because what I do is in this case, instead of passing this return data up to the application, I replace it with a bunch of garbage. And so let's see what the garbage I used is. You can see that actually this is interesting because this is a case I haven't run into before. The nice thing about fuzzing is that I use truly random data, so you never know what you're going to get. You can see that I've actually modified some of the metadata here. So before the bytes were 00, D2, 5D, etc. Well, what I actually sent to the middleware is not those bytes up to, it would appear, the 5th byte, and then the rest is the same. So what's interesting is that I didn't change the GUID at all, which shouldn't matter, but I also didn't change the length byte, which I usually do. And so what that tells us is that this metadata does something pretty important, because as a result of fuzzing this metadata, I caused a heap buffer overrun in the middleware. That's what this access violation is. And if you look at this address here, 98400, that it tried to write to, that's in the process heap. So that's pretty interesting. There are a couple of important takeaways here. One is, this vendor clearly assumes that it can always trust input from its smart card, which you might think is a reasonable assumption, but it's absolutely not. For one thing, no software has any business making assumptions about trusted input. I mean, that's bullshit, right? You can't do that. 2, cards in general, and actually including the DoD smart card that you mentioned, and this one, now have VMs on them. So what that, as in a virtual machine. So what that means is that you can write a Java applet or a .NET applet, like write some C#, in like 3 lines of code that would actually do this, what I just showed you, without having to install any software on the PC. You wouldn't have to install my hook. You just write the bogus applet, replace the applet that's on the card with that, and now you can send all the crap you want to through the middleware. And it's not expecting it, obviously. So what that means is that if you walk up to a Windows PC that already has the driver loaded, or already has the driver ready to install for one of these interface devices, and that already has the middleware for this card, and you have a bogus applet on your card, you're going to take out this process. So that's pretty fun. I recommend that you go home and play with that. That's it for this demo. Any questions about that? OK. Sorry? Yeah, so if you want to play with it, I'll give you the code. I am going to scrub the code for the vendor-specific pieces. I don't want to kill this vendor any more than I have to. And by the way, this vendor, I have engaged in responsible disclosure here. This vendor knows about the bug. I was told it's fixed, but honestly, I didn't verify that. And it's obviously not fixed on my Vista PC, so. Oops. OK, the next demo is hacking crypto. This is just a quick demo. And again, now we're back into the territory of the of the samples that I did for Microsoft, or that my company did for Microsoft. What I wanted to